All right, hello everyone. Welcome to Severe Weather Safety 101 to kick off our Severe Weather Awareness Week. We're going to go around and do some introductions here quickly before we get started. So my name is Rachel Gutierrez. I'm a meteorologist at the Weather Service in State College. I started back in May, so I've almost been here a full year, which is really exciting. I'm originally from the Chicagoland area, so of course I love deep dish pizza. Shout out to anyone who's originally from the Midwest or Chicago. And we're very excited to be talking about severe weather safety here today with you. So I'll pass it off to Mike.
Hi, everyone. Thanks for being here. My name is Mike Colbert. I'm the severe weather focal point at the office. I'm originally from Long Island, New York, so I'm a big fan of New York style pizza. And did my undergrad at Stony Brook University in Long Island, New York, and then a master's degree at Penn State. And I've been at the Weather Service now for 3 years. I'll turn it over to Miranda.
Hi everyone, my name is Miranda Bidding. I'm a senior at the University of Delaware studying meteorology and climatology. And this semester I've been volunteering at NWS State College. And next year I will be starting my master's in meteorology at Penn State. I'll pass it over to Connor.
Good evening, everyone. My name is Connor Chapman. I am a grad student at Penn State University, and I am right now studying geography and climate science. I did my undergrad in meteorology at SUNY Oneonta in the tundra of upstate New York. I'm glad to be here volunteering with the Weather Service for this semester.
Okay, so I'm going to start us off with a little bit of an introduction here. So this talk obviously will be about severe weather safety. A little bit of ground rules first for attendee engagement. If you have any questions that come up, please feel free to type them into the question section of the GoToWebinar window on your screen. That should be probably on the right-hand side of your screen. At the end, there's also going to be a time for question and answer. You can use the raise your hand feature if you have a question. And I also want to point out, again, Rachel mentioned at the start that there's handouts that are attached to the GoToWebinar panel as PDFs. You can feel free to download them and use them as a reference for this call and for the future. There's some useful links and some other good information on those handouts. Okay, so before we get into things, I'll talk a little bit about who we are at the National Weather Service. The National Weather Service is a branch of the federal government. It's actually part of the Department of Commerce, and we are here to protect life and property for people in the United States. The Weather Service office in State College, Pennsylvania, serves central Pennsylvania, and we are comprised of 14 forecasters as well as 6 electronic technicians and IT support. So they are responsible for maintaining the radar that runs all the time and collects atmospheric information. They're also responsible for maintaining the automated surface observation sensors at the airports, and they're responsible for maintaining everything in the office, all the computers, keeping them hardware and software up to date. And then other people that we have at our office, we have a hydrologist who is the go-to person for anything related to rivers and hydrology and flooding in our area. We have a science and operations officer who's responsible for training, making sure that everybody on the staff is trained with the latest science and technology. They also work on a lot of projects that are science related. A lot of us do in the office, but the science and operations officer is kind of the head of that program. And they also go to quite a few conferences just to make sure that they're caught up on the latest and greatest science. We also have an observations program leader who kind of leads a program of observers around the area that are volunteers that provide us with information of what the high and low temperature and precipitation was, rainfall and snowfall amounts. We use that for climate records as well as for verifying what's going on a daily basis. We have a warning coordination meteorologist who is responsible for maintaining relationships between our office and the emergency management community and the Department of Transportation and all these other partners that we have, which is critically important for a weather-ready nation. Of course, our forecasts, even though they're not probably 100% accurate right now, but they're very close. And even if they were 100% accurate, if we don't get that message out to the right people and they don't do the right things with that forecast, those forecasts can fall flat on their face and the public can still be unprepared for events. So that relationship between us and our partners is critically important. We have an administrative assistant who's like the secretary in charge of paying the bills and all that. And we have a meteorologist in charge who overlooks everything in the office and makes sure everything gets done. So that's kind of how we're laid out. And as far as staffing goes at our office, and we are open 24 hours a day, 7 days a week, every day of the year, including holidays and all that. And again, our goal is to provide forecasts and warnings as well as maintain our critical systems. So that's about, that's all we'll get into about who we are. And then this next section is going to be a primer for the rest of this course, which is the weather safety, summertime weather safety. But before we go into that, we wanted to provide a little bit of a background about thunderstorms. And this background here, actually on the slide itself, this animated satellite loop is actually from a cluster of thunderstorms that came through Pennsylvania last summer. I think the date was June 4th. And it actually developed into what we'll call a mesoscale convective system, a big organized line of thunderstorms with lightning you can see displayed there. That's actually detected by the satellite itself, which is pretty awesome technology and pretty new technology, only just a few years old. But that's a loop of a series of thunderstorms that produce a lot of thunderstorm wind damage. And we'll get into a little bit about different types of thunderstorms in these coming slides. Okay, types of thunderstorms. So there's three main types. The first type is the ordinary single cell. Those are the type that last the shortest duration and they usually create the least amount of damage. Then the next step up after that is the multi-cell or multi-cell cluster or line. And this is when there's not just one cell that pops up, there's going to be more of a like a system, maybe a series of cells that are kind of connected. They're not just discrete, they're connected, and sometimes they form into a line. Sometimes they go on and produce more wind damage. So we'll talk a bit about how those are formed. And then the last one, which if you're a fan of severe weather, you probably have heard storm chasers and the like talk about this. The last type is a supercell. And that's similar to a single cell, but it's organized in a way that allows it to live for a long period of time, become very mature and organized, and can go on to produce some of the most severe weather that there is, including very large hail and strong tornadoes. Those are most likely to happen with a supercell compared to the other two types of thunderstorms. So we'll go through each one, and we'll start off with a life cycle of an ordinary single cell thunderstorm. So again, this is going to be the type that's least severe. So the first step for the ordinary single cell thunderstorm is the towering cumulus stage. And this is actually kind of similar to what we've seen in the sky over the past couple of days. We've actually seen some relatively tall towering cumulus clouds, not quite as tall as they can get in the summertime, because we still don't have maximized incoming solar radiation from the sun at this point. We're still in the springtime. Just a month ago, or actually just a few days ago, it was snowing. So we don't quite have that surface heat yet. But the idea is the warmer the surface of the Earth gets and the colder the atmosphere is above it in comparison to the surface, that temperature gradient between the ground and what's above allows for instability, which allows clouds to grow and become tall and potentially become thunderstorms. Because warm air parcels, or little pockets of air that rise up from the ground, they are, warm air is less dense and more buoyant, will rise compared to cold air. That's why whenever, when they teach fire safety, they teach you to get down to the ground. If there's ever a fire in a home, you want to get down to the ground so that you're not exposed to the heat and the smoke, because hot air rises. It's the same thing in the atmosphere. hot air from the surface will rise up, and if there's cold air aloft, it'll continue to grow. And that's how we start here with the towering cumulus stage. And then if if there's a lot of instability and a lot of moisture in the atmosphere, you can become, the cumulus can become a mature cumulus and eventually a cumulonimbus cloud. And in that stage, you have an updraft and you have moisture that's condensing into liquid cloud droplets. There's also going to be probably some ice cloud particles up here at the top. You can see that the clouds are becoming a little bit more glaciated or kind of crisper on the edges here. That's a sign that there's ice at the top of the cloud. And this is all a sign of a vigorous updraft. And an updraft will become stronger and stronger, essentially until there's precipitation within that updraft in the form of rain and sometimes graupel, which is like little frozen raindrops, and sometimes hail, which is start off with the graupel and then you get more and more ice around that. You can have some hailstones, and all that precipitation starts to weigh down on the updraft itself, and you get a downdraft. And in the case of an ordinary single cell thunderstorm, that downdraft eventually is going to come down, and this little cold front here signifies a rush of cold air coming down with the downdraft. And ultimately, in the case of a single cell thunderstorm that's ordinary, this cold air is actually going to undercut that surface updraft. And because this air is cold, it can't rise as efficiently. And when it undercuts the updraft, that storm essentially is going to die out, because that updraft can no longer rise. It's no longer buoyant. It's too cold. And that leads to the last phase of the ordinary single cell thunderstorm, which is the dissipation stage. And since there's no updraft left, you're just left with a little bit of cloud particles and whatever precipitation's left here at the top. And it ultimately falls down to the ground, or if there's dry air at the surface, it may even evaporate before it gets down to the ground, as is shown here in this picture. And that storm is over. And it never got really mature or well developed enough for severe weather to happen in most cases. And this could all happen in a span of just 20 to 40 minutes. So they're pretty short-lived. So that's the nuts and bolts of an ordinary single cell thunderstorm. Now moving on to a multi-cell cluster. It's kind of similar, you can see in this diagram, a little bit similar to the single cell, but you can see all stages of it kind of happening at the same time. In the middle here, there's the mature stage. On the left here, there's the towering cumulus stage. And on the right, there's this dissipation stage. But the thing that's happening here is, as opposed to the ordinary cell, when there's multi-cells, there's usually what we call wind shear in the atmosphere, which is a difference in wind speed with height. And what that does is it allows the air to kind of overturn on itself. And if the air is overturning on itself, it can actually put some resistance on one of those sides of the cold pool as the cold pool rushes out. So if a cold pool is coming along like this, and then there's wind shear like this, where the air aloft is moving faster from left to right than it is at the ground, the air will kind of overturn and at the surface put some resistance up against that, actually support development along part of that outflow boundary. And that's what's happening on this next slide with the back building multi-cell cluster, where the cold pool is actually moving out, and then there's some resistance on that, and there's continually new towering cumulus clouds being formed on one of those sides of the cold pool. So this is the whole, cold pool is kind of like this, and you get a new line of storms forming along it. So yeah, in the case of a back building multi-cell cluster, which is what we have here, upper level winds are going to carry the first cell downstream, with new cell forming upwind of the previous cell. And in this case, where the winds aloft and the surface inflow are in two different directions, you can have back building, which we see in this case, and this can actually lead to flash flooding, because you have a storm that, instead of lasting 20 to 40 minutes, could back build on itself and could last upwards of an hour or 2 hours or even longer in some cases. And that can drop, if you have, say, 1 inch to 1.5 inches per hour rainfall rates, over a course of just a few hours, you have several inches of rain. And that can be a big hazard. So these multi-cell clusters they really can be a lot more troublesome and lead to much higher impacts than the ordinary single cell storm. And then there's also different classifications of the multi-cell clusters. There's something called a mesoscale convective system, which is a large, long-lived multi-cell cluster that kind of moves along and it's kind of organized into one long-lived system. They can be even subclassified farther into mesoscale convective complexes, and on the higher end, something called a derecho, which is known kind of like a land hurricane, where winds are often 70 to 80 miles per hour with those. They're pretty rare. They only happen just a few times per summer anywhere in the United States, and then in Pennsylvania, they usually only happen once every several years, once every 5 to 10 years or so. So they're pretty uncommon, but that's kind of like the higher end, more extreme case of a well-developed mesoscale convective system known as a derecho. And any linear mesoscale convective system, you may have heard the term squall line thrown around. That's all that is. That's a line of thunderstorms. So a multi-cell cluster that was organized as a line. And then the third phase here is the supercell. And this is a different class of thunderstorms. This is a diagram of one here. So what you see here is a big cumulonimbus. It has a very robust, long-lived updraft. Has a wall cloud usually towards the bottom, which is a sign of strong rotation and also kind of the base of that vigorous updraft. So the updraft probably starts right around here at the base of the wall cloud and then goes up through the cloud all the way up to this overshooting top. Whenever you see an overshooting top at the top of a thunderstorm, it doesn't even necessarily have to be a supercell. Supercells usually have them, but even some squall lines and ordinary cells may have them from time to time. The overshooting top is a sign that the updraft is very strong and is overshooting its equilibrium level, where that buoyancy that I talked about, where the warm air keeps rising because it's warmer than the cold environment around it, eventually that parcel becomes the same temperature as the air around it, and typically that's where the updraft stops. But in a supercell or a very strong thunderstorm updraft, that updraft has so much momentum that it blows right by that equilibrium level, and you end up with this overshooting top. And you can see those on satellite imagery too. Whenever you see that, either visually or based on satellite imagery, you know that storm is exceptionally strong. This anvil is occurring here at the top of the equilibrium level. So that's again where the temperature of the updraft and the surroundings are the same temperature, and that's where you typically get that fanning out, other than where you have the overshooting top. And then this flanking line, this is kind of similar to in the multi-cell cluster diagram, there was this towering cumulus phase. Really the same thing going on here in the flanking line, where there's a cold pool underneath it and an updraft being kind of lifted up above there, and sometimes there can be development along this flanking line as well, but not always the case in the supercells. Sometimes the supercells is really just one dominant updraft that overtakes everything else. I mentioned that those updrafts in the supercells can be very strong. They can attain speeds of over 100 miles per hour pointed straight up against gravity. So that's pretty remarkable. And they can produce giant hail, even gargantuan hail. Sometimes I think that the largest hailstone ever was measured to be about the size of a soccer ball or something close to that. Usually not that tall. Usually, especially around here in Pennsylvania, we get a lot of pea-sized hail, and then on the severe scales, it's typically between the size of a quarter, like the coin a quarter, or the most I've seen since working at our office within the past 3 years, the biggest I've seen was about 2-inch diameter hail out in east central Pennsylvania. And then the downdrafts can also produce winds in the horizontal direction that you would feel sometimes in excess of 100 miles an hour. That's again on the high end, typically closer to 60 or 70 miles per hour. But supercells can also produce tornadoes, and the most ideal conditions for supercells occurs when the wind turns clockwise with height. So there's wind shear that's not just speed shear, but also directional shear. And that clockwise turning with height allows for actually allows for the turning of the atmosphere to become oriented with the updraft itself, and you can get overturning the atmosphere like this to become vertically oriented, and then the storm itself starts spinning, and when you get a rotating updraft, that's how a supercell comes to be. There's two general classifications of supercells. They can be low precipitation or high precipitation supercells. The ones around here that we typically get would be on the higher precipitation side, where if there was a tornado, it would probably be rain wrapped and you wouldn't be able to see it coming. Low precipitation supercells occur usually out on the southern part of the Great Plains in the central and western U.S., where there's a drier air. They're closer to the desert regions, and that drier air allows for these clouds to be higher based, and they can be very photogenic supercells, and you can actually see the tornadoes with them. But yeah, around here, usually they're somewhere in the middle, but leaning a little bit towards the higher end precipitation type of supercells. So we talked about different types of thunderstorms, and we talked about how supercells produce a lot of the severe weather, and multi-cell clusters and squall lines also produce quite a bit of severe weather. But what actually makes a storm severe? So go through a little bit about that. So any wind that's above 58 miles an hour, 58 or above, would be classified as severe. And if you're wondering where we get 58 from, it's not a round number. Well, it comes from 50 knots. 50 knots translated to miles per hour is 58 miles per hour. So if it has wind of that speed, or if it has hail, it doesn't need both, it needs one or the other. So if it has hail of 1 inch maximum dimension or greater, that could also make it severe. And that's about the size of a US quarter. And of course, if it has a tornado, regardless of how strong that tornado is, it would be considered a severe thunderstorm. And if we think that the storm has a tornado, we're not going to put a severe thunderstorm warning on that storm. We're actually going to put a tornado warning on that storm. But it's still considered severe. And then other threats, every thunderstorm that there is, obviously if it has thunder, it has lightning. That's what makes the sound of the thunder. So that's a threat always to consider with a severe thunderstorm. And flooding is another case, especially for those back building multi-cell clusters. So go through a couple cloud examples here. So if you were to see something like this on the left here approach you, this is actually known as a shelf cloud, and we see quite a few of them around here. They're very common. I'd say most of the thunderstorms that come through have a shelf cloud associated with them. And yeah, this is what they look like, and what you can imagine here is a downdraft coming through here with usually with heavy rain, and there could even be some small hail in a mesoscale convective system, which is a form of the multi-cell type of thunderstorm. So yeah, you have your precipitation coming down here, rain and maybe small hail and colder air, and that's rushing out towards the surface. And that downdraft of colder, denser air actually forces air out ahead of it to rise over it like this. So the flow of air, if you kind of follow my pointer, downdraft like that, and then some air out ahead of it coming up like that. And that rising air above it actually is what produces the shape of this cloud. It's kind of a stable looking, smooth cloud, which is definitely a sign of a shelf cloud forming on colder, stable air. And if you see this coming, you can count on some strong winds and heavy rain and small hail coming your way. Now, a supercell, this is kind of zoomed in on the wall cloud, so really zoomed in. If I go back just a couple slides here, I'll just show you what part of this storm we're zooming in on here. Go back even one more. Yep. So we're all the way zoomed in on this. So the scale of the supercell, again, is huge in comparison. But if you're standing right here down by the wall cloud and pretending that in this case there's no tornado, most supercells don't have tornadoes. It's only less than 10% of supercells actually have tornadoes. This is the wall cloud. And then we'll go back to our current slide and yeah, zoomed in on that wall cloud here, this is what it looks like in person. You can actually almost get a sense of the rotation around this thing. With the clockwise rotation, you can see kind of striations in that wall cloud. You can see very low hanging clouds here. And if you ever see a wall cloud, you know that that storm is a supercell and has a higher chance of having large hail, a higher chance of having strong winds, and also a higher chance of potentially having a tornado. It doesn't look like there's one in this particular example here, but if you ever were to see a funnel or a tornado hanging out of a wall cloud, you know that that storm, you don't want to mess with that. You want to seek shelter immediately. Okay, so a couple of examples here on radar. This is a mesoscale convective system, also known as a squall line here, since it's oriented in a line. That's what it might look like on the radar. And I should say that this is radar imagery, radar reflectivity, actually. So the brighter colors actually represent larger particles and or larger concentration of particles. So it can mean that the particles are bigger or that there's just more of them per unit volume. So regardless, this is showing that there is heavy rain and maybe even some small hail with this line of thunderstorms. And also, given what we know about mesoscale convective systems and the ways that they form into squall lines, we know that this probably has strong winds with it too. And then this is what a supercell looks like. It looks really different. And I should also say that this is much more zoomed in than this image here on the left. The supercell is usually smaller than a mesoscale convective system, so we're just zoomed in. But if you ever are looking at radar and you see a hook echo like this, that's where the rotation is. That's where this wall cloud would be. That's where a tornado might be, but a hook echo is not necessarily indicative of a tornado. You can have a hook echo and no tornado at all, but it does mean that there is a strong updraft, and that updraft is rotating. And potentially, if conditions are right, if there's enough moisture and a few other ingredients come into play, then maybe there could be a tornado too. Okay. So for the next section, I'm actually going to turn it over for weather hazards. All right. Thanks, Connor.
Yeah, thanks, Mike. Bear with me a second. Trying to click it forward. Okay, so I'm going to talk a little bit about lightning, another that's often associated with severe weather. What I want to mention before anything, before I dive in, is one thing that's really important to think about lightning is that it's not a criterion for severe thunderstorm warnings. So severe thunderstorm warnings just take into account hail, wind, and whether or not there's a tornado. Lightning can occur in any thunderstorm, whether or not it's named a severe thunderstorm. Likewise, a severe thunderstorm could, in theory, occur that doesn't contain too much, cloud to ground lightning. They're often associated with one another, but note that that's not lightning is not an element of severe thunderstorm warning. So just because a storm isn't warned, you're not getting an alert. Lightning is still a threat. Can be a threat in any thunderstorm. Think, the Florida in the summertime, how thunderstorms will pop up every day. Might not be hail, might not be wind, but plenty of lightning. So that's why it's super, super important to be prepared for what to do when thunder roars. So lightning is the second most deadly form of severe weather. That, again, is why it's so important to have a plan for when you're going outside. Obviously, check the weather beforehand. I have a plan too for what's your plan B if you're not able to get indoors, if you're not able to seek shelter. Are you able to get into a car? Are you able to seek another form of shelter? Making sure that we're following some tips that I'll bring in a minute. So always just have a plan for when thunder roars. Always good also to make sure you have wireless emergency alerts enabled so you can get important weather information. It's the first hazard to arrive and it's the last to leave. So, you know, a thunderstorm might be rolling in. Rain might not come for a while. You might not get wind. In fact, the thunderstorm itself could kind of brush by you, maybe to the north, to the south. You might not get the full extent of the wind or the rainfall that's associated with that thunderstorm. You can still experience lightning. So that's why it's super important. If you can hear thunder, typically the rule of thumb is if you can hear thunder, you want to find some sort of shelter. You want to get inside. You want to get away because you are in range for lightning strikes. Funny, you know, well, not necessarily a super fun fact, but just something to think about. People think, you know, oh, you know, there's no chance of me ever getting struck by lightning. The odds are relatively slim, but higher than the odds of winning the lottery. It's actually more common than is ideal. So it is definitely a threat, particularly for outdoor activities like boating, golf, and so forth, places where you're out in the open. That's why you really, really want to keep in mind what your plan might be to make sure that you're not in that situation. And lightning is super, super powerful. They can, the average strike contains 300 million volts. So really, really, really powerful. That's why they can be so deadly or cause serious, serious bodily harm to folks who are impacted by lightning strikes. So where does lightning occur? In short, pretty much everywhere, as you can see by this map. This is a climatology map, so just like an average distribution of how often lightning occurs by area. So you can see some of the global hotspots, typically in the tropics, you know, the Congo, the rainforest there. You know, you'll get thunderstorms all the time. But you can also see here in pretty much all the central and eastern United States, including Pennsylvania, lightning is relatively common, at least in thunderstorms, because especially as we're getting into this time of year, April, May, June, getting into peak thunderstorm season, lightning is often associated with these thunderstorms. So we are by no means excluded from lightning hotspots just because we're not in the tropics. And that's another thing to think about too, that globally, you know, except for some parts of the ocean and near the poles, globally lightning can occur anywhere. But the central and eastern United States experiences a higher than normal compared to other parts of the world distribution of thunderstorms and thunderstorm-related activity, including lightning. So you know, keeping that in mind, that maybe we don't see the crazy tornadoes as often like you see in the Great Plains in the South, but we still do experience lightning. It still is indeed a hazard here. So lightning essentially, it's a form of electricity. It's applied electricity there. If you're ever taken a physics class in high school or maybe college, thinking about electrical charges and so forth. Typically, lightning occurs as negative lightning 90–95% of the time. Transfer of a negative charge from the cloud to the ground. And you can just see a little diagram here that shows the charges kind of separating in the cloud. So the surface is positively charged. The positive charges also in the cloud go towards the top, and the negative charges towards the bottom. And then there's a transfer, there's a charge between the cloud and the surface. It's a good time to point out that nearly all lightning is what we call cloud to cloud. So that's lightning that does not impact the ground. It's just charge transfers between clouds in the atmosphere. Still a hazard for aviation interests. Things, you know, pilots want to keep in mind. But just because cloud to ground lightning is so rare, when it does occur, it can be very damaging. That's why you want to just keep in mind how it occurs too, and looks for oftentimes tries to find the highest object relative to a given area to connect with. So that's why you think of trees, or why lightning rods were invented. The theory behind that is to deter lightning perhaps from striking another part of your property. If you have a given area, you know, put a lightning rod up to make that the highest feature on your house. The theory being that, you know, if lightning strikes there, then that can be the ideal target for lightning to then distribute the charge into the ground and avoid the potential for lightning striking parts of your home or trees or so forth. Obviously not a guarantee, but that's some of the logic behind that. But then ultimately, a lightning strike forms between the negative charges near the bottom of the cloud and the positive charges near the ground. So that's how most cloud-to-ground lightning occurs, is negative lightning. A less common but much more powerful form of lightning is called positive lightning. And so it's basically the flip-flop there of what we just saw in negative lightning. So the positive charges are at the base of the cloud, negative charges are on the ground. Can be 4 times as powerful as negative lightning. So just because they're less common, these lightning strikes can be much more powerful, very, very dangerous, can be associated with really strong thunderstorms, near a tornado, even thunder snow too. If you've ever seen that on TV during powerful winter storms or snow squalls, that sometimes lightning and thunder can be associated with powerful winter storms there. Positive lightning has been seen there too. So technically a year-round threat. This is particularly the time of year there. Now, of course, you're not necessarily going to get alert on your phone saying, positive lightning alert versus negative lightning alert. But it's just something to keep in mind that not all lightning is the same. It's not a one-size-fits-all type of thing. And that certain lightning strikes can be much more powerful than other sorts of lightning strikes. And why it's always important just to keep in mind what your plan is for when you're going outside and you know that there's a potential for thunderstorms later in the day. Another thing to mention, as we said, lightning is the first to arrive and the last to leave as far as thunderstorm activity. These positive lightning strikes, up to 25 miles from the center of a thunderstorm, these can occur. So that's why, even after the thunderstorm passes, you can still hear the thunder. It's a good idea to make sure you're somewhere safe, somewhere protected, somewhere enclosed before venturing back out. And these are sometimes called Anvil Crawlers too. As Mike was saying earlier, with some of the most powerful thunderstorms, how you get that anvil that forms. Sometimes these associated with like the upper reaches of super strong thunderstorms. So that's why if you see this picture here, how this is, I'd guess several miles long, maybe 6 miles long here. So intuitively, a very powerful lightning strike here. So these are particularly powerful lightning strikes, but all cloud to ground lightning can be a hazard, and make sure you're prepared for all types. Just know that it's not a one size fits all type of thing. Just a couple do's and don'ts, some tips for staying safe for when thunder roars. So ideally, you'll be at home, maybe in your car, somewhere that's safe when thunderstorms occur. But that doesn't happen all the time. Sometimes thunderstorms creep up seemingly out of nowhere. We're not prepared for it. If you didn't check the weather in the past couple of hours, you're not expecting it. What do you do when that situation happens? You want to find a place that's enclosed. So pavilions and picnic shelters, while you might think, okay, there's a roof over, there's some sort of shelter, and while that's helpful, it's not enclosed, and so it's much better to be in a place that also has 4 walls, is enclosed, so that you don't get any indirect lightning strikes. It's just very, very important to find a space that is enclosed to give you maximum protection. Same thing, vehicles too. So probably goes without saying, but if you're in a convertible or in a open roof Jeep, gonna want to close the roof there. Make sure it's all enclosed to provide maximum protection. Again, things that are pretty basic, but very, very important. You're not going to want to be touching plumbing, not going to want to be touching metal equipment outside. Definitely if you're out golfing, you might not want to be standing up in the open field, and definitely don't want to be holding on to that golf club, because that is a target. One, when you're swinging and you have an extra few feet above your head, that makes you that much taller, and 2, it's made of metal. So just another thing to keep in mind. Probably not going to want to take a shower or bath or use plumbing, or at least make contact with plumbing, just because water is a conductor. It's not as powerful of a conductor as forms of metal, but it still is a conductor, and you don't want to put yourself in that situation if lightning strikes as you're using a plumbing appliance, getting your hands wet or something. It's just an extra layer of precaution there to keep yourself safe. Rubber shoes will not necessarily protect you. Sure, it's better than having metal shoes, but it's not a blanket protection of going outside with rubber shoes, and then you're not going to get any sort of charge from the ground. What you need to do is make sure that you are in an enclosed space, not making contact with the ground, or if you are, out in an open field, lowering yourself as best as possible so that you're not making yourself as much of a target. With that said, while you do, if you find yourself in an open field on the golf course, anything like that, or out mowing the yard and you can't get back inside, you definitely want to make sure that you're lower to the ground. It's definitely a safety thing, but you shouldn't necessarily go under a tree. And this is why. So some of the common logic is that, okay, well, I want to be right near a tree because a tree is way taller than I am. So if lightning comes, it's going to strike that tree first and not me. And that theoretically is correct. Lightning is taller than you, so lightning is going to want to hit the tree first. But the charge could come through the tree and hit you if you're underneath that tree or nearby that tree. So could make you even more of a target if you're very close to a tree when it does get struck by lightning. So that's just another thing to keep in mind. Not that you want to be standing as in the open as possible, but standing right next to a tree, right underneath the tree, can actually be more risky than otherwise. This is just a chart of lightning fatalities over the years, for the past 10 years or so. Fortunately, as of the time of collecting this graphic, no lightning fatalities so far this year, and would love to keep it that way. Males are about 3 or 4 times as likely than females to be fatally struck by lightning. I am not a health expert, so I can't speak to why that is. But regardless, just gives just goes to show why it's crucial to make sure that you always have a plan for when you're going outside, when you're outside of the house or outside of the car, what you're going to do when thunder roars. That's it for me for now. I'll be passing it on.
All right, thank you, Connor. See if I can control this. Okay. So it might not surprise you to know that hail is the costliest form of severe weather. Again, I said that's not a surprise because it's literally balls of ice plummeting from the sky. So, it's easy to imagine that could damage your car, your house, etc. And hailstorms can take one of 2 forms. There can either be a small number of very large hailstones kind of falling sporadically, or they can be very small hailstones, but very many of them, and they kind of start to accumulate like snow. Or, the hailstorm could be somewhere in between. But the point of that is, if you're getting those very large gargantuan hailstones, they're not going to pile up and accumulate like snow. That would be crazy. There just isn't that much mass up in the clouds to fall. So you might know that it's very difficult to forecast the exact hail size. You may not get like, oh, it's going to be 1.25 inch hail falling. And the reason that you don't get that specificity is that hail growth is a very complicated process. There are a lot of different ingredients that go into it. The 3 main things that you'll need to get hail actually falling at the ground is you'll need an embryo. So that's going to be a piece of ice, snow, or dust up in the cloud above the freezing level. And that's where the supercooled water droplets actually collect and start to grow and freeze. So again, the next thing you'll need is ample supply of supercooled liquid water. That's what freezes and then gathers more and more layers and creates the larger and larger hailstones up in the cloud. Now, to support this growth, you're going to need a strong enough updraft, because if you think about it, the bigger the hailstone gets, the more it is pulled down to the earth by gravity. So to counteract that, you'll need the strong updraft, keeping it up there in the cloud. And the longer it's up in the cloud, the more it can grow and the larger it will become. So that lends itself to residence time. So longer residence time, larger hail. And temperature is also important. For hailstones to form, you need that large layer of above freezing level in the cloud. Okay, so I'm just going to talk a little bit about how hail forms. So like I said, up here above the freezing level, you have your hailstone embryo. That's your piece of snow, ice, or dust, and that is where it all begins. That allows the supercooled water to come in and freeze, and that is your base level, and that keeps growing and growing. So then as it gains more mass, it's going to want to fall, but then the updraft comes in and pushes it up again, so it's able to stay there for longer, collect more and more water, and it kind of grows in layers. If you've ever seen pictures of a large hailstone cut in half, you could see it kind of looks like an onion with all the different layers. So then finally, when it's large enough that the updraft no longer keeps it up there, it then falls down in the area of the downdraft with all the other rain, and it can reach pretty significant terminal velocities. So if it's a large hailstone, you definitely don't want to get hit by it. Okay, so here are just two examples of the different types of damage that hail can cause. So on the left, this is definitely a case of large hail. You see it would be fewer amounts of hailstones, but they appear to be very large because they created these dents in the windshield. I actually was storm chasing in Texas a couple of years ago, and we were driving around this supercell thunderstorm, and it was really cool because driving around the outside, we got to see the structure. But, you know, I was like a sophomore in college. I wanted to drive right in, be in the center of all of it, but that just wasn't allowed because the storm was producing hail, and it would have caused significant damage to our vehicle if we had driven straight through. So we were able to wait for it to pass and then drive in the area that it hit and look at the hail then. And I'd say the storms we chased, we saw up to about quarter size, maybe a little bit bigger, but nothing too crazy. But then on the right, this is a totally different case. This looks like a much greater number of hailstones, but they're much smaller. And they actually are accumulating kind of like snow. Like if you just took a first glance at this, you might think it's snow, but it actually has a very different structure because snowflakes are very, very small, and even the smallest hailstones are going to be much larger than snowflakes. Now, on the left here, this obviously causes a lot of damage just by pure impact, but on the right, this can also be dangerous because if this accumulation of hail were to melt, it could then cause flash flooding down the line. So both can be dangerous situations. All right, so here's a video of a particularly violent hailstorm that happened in Arizona. You can see just how intense this is. Now, we usually don't get really intense hailstorms like this in Pennsylvania, but if you go out west, out to the plains, they do get some pretty large hail out there. Yeah, I would not want to be outside during this storm. Okay, so let's talk some do's and don'ts. Obviously, you're going to want to get inside. I think that's common sense. If a storm like the one in the video were happening, you would want to go inside anyway. And general rule of thumb, if there's a thunderstorm, you should be inside anyway to avoid any of the very dangerous consequences like lightning, hail, etc. The other thing is you're going to want to stay away from windows, because if you notice, the hailstones weren't falling straight down. They're kind of being blown all over the place by the strong winds in the thunderstorm. So you're also going to want to be away from the windows in case hail comes in and breaks them. You don't want to be standing next to it when that happens. And this isn't directly related to hail, but one of my meteorology professors, he actually was leaning over a sink right next to a window watching a thunderstorm, and some generator out in the yard got struck by lightning, and the current traveled into the metal sink he was leaning over and threw him across the room. So he got struck by lightning in his own house. He was totally fine, still alive. He survived, but the first thing that ran through his mind was, I can't wait to tell my meteorology students about this. So, even if you're inside, you should take extra precautions. You got to stay away from the windows. Don't touch anything electrical. Just, use your common sense. And okay, so let's say you're camping and you don't have a building to go to. Like, what do you do? The first thing, you're going to want to find shelter if you can. This may not always be possible. So then if there's no shelter, your priority should become covering your head, because clearly it's the most important part of your body. And if there's large hail falling, you're going to want to protect your head, because the terminal velocity on large hailstones is great enough to break bones, could give you a concussion, and could even kill you. According to Noaa, only 4 people since the year 2000 have died directly as a result of hail, so that is a low number, but it's not 0, so that's something to keep in mind. All right, so now I'm going to talk about wind. So in this section, I'm not talking about tornadoes. Instead, I'm talking about the straight-lined wind damage resulting in the downdraft. If you remember how Mike C was explaining the structure of a thunderstorm, you have your updrafts on one side and your downdrafts on another. So in certain cases, the downdraft can be very strong. And if you think about it, it's air moving down from the cloud and spreading out when it hits the ground. So these can reach very high wind speeds. And when that happens, we call them microbursts or macrobursts. And the difference is that microbursts are pretty small in size, less than 2.5 miles across, and they usually only last for about 2 to 5 minutes, so they're very short-lived, but they can be very strong and can produce winds up to 168 miles per hour. Now, macrobursts, they're pretty much the same thing, except they're larger in size, so they're greater than 2.5 miles across, and they can last a little bit longer, 5 to 20 minutes. They can produce winds up to 130 miles per hour, which, if you're familiar with the Enhanced Fujita scale, this is equivalent to an EF3 scale tornado damage. So I find it interesting that everyone knows about tornadoes. They always make front page news, but downbursts, like microbursts and macrobursts, they can be just as damaging, and they actually happen roughly 10 times as often as tornadoes. So it's just really interesting that everyone knows everything about tornadoes, but a lot of people haven't even heard of microbursts. So I'm glad I got the opportunity to talk about it right now. All right, so on the left here, we have a radar image. This is called Radial Velocity. And just to orient you, that black circle right there is where the radar would be. And a green color is winds moving towards the radar, whereas red is moving away from the radar. This doesn't necessarily mean that the winds are moving in a perfectly straight line towards or away from it. It just means that a component of the wind direction is either toward or away from the radar. For example, if you have an area of winds parallel to the radar, not moving towards or away from it, those show up as that black color right there. And now we're talking about downburst. So again, that is the downdraft hitting the ground and spreading out in all directions when it reaches the ground. So it's actually quite easy to spot on a radial velocity radar image, because over here you have this red circle, which is anomalous to the surrounding flow. This area is moving towards the radar, whereas this part's moving away from the radar. And over here, it's a little bit more difficult to spot, but this area of wind speed is actually stronger than the surrounding flow. So what this tells me is that the downdraft is right here, and it's just spreading out when it hits the ground. All right, so here's another video of a downburst that actually happened in Lancaster, PA last June. And this would be an example of a wet microburst, because the fact that you can see the wind tells you that there is precipitation, because you can't see air. What you're seeing is the water moving all around. You can just see how intense those winds are. It's complete lack of visibility at this point. If you didn't know any better, you might see this and think a tornado went overhead. So this just goes to show that we do get severe weather here in central PA. Even if we're not getting all the tornadoes, there are a lot of impacts to be aware of and know how to deal with. Just a complete lack of visibility. It's crazy. All right, so wind do's and don'ts. Obviously, I'm preaching to the choir, stay inside. Any thunderstorm, any severe weather event, you're going to want to be inside. Another added precaution is you're going to want to stay away from windows and doors. Basically treat this like if a tornado were to come, because again, it's strong winds, similar impacts. You want to be away from windows and doors in case they blow over or break. You don't want to be right next to it. And like a tornado, you're going to want to be in your basement if you have one. If you don't, just try to get close to the interior of your house, away from doors and windows. Also, you don't want to be in an exposed building like a pavilion or a picnic shelter, because if you think about it, if you're underneath one and some very strong winds come in and it breaks, you definitely don't want to be under that. You're actually better off without shelter if it's going to break. Also, same logic, don't be near trees. You don't want to be near them because they could get struck by lightning, but also because if a strong microburst were to come in and knock the tree over, you want to be as far away from it as possible. So again, say you're camping, you didn't check the weather, you got some extreme downbursts coming your way, you're going to want to be away from the trees, and you do want to seek shelter, but you want to be a little bit picky about those shelter. An exposed pavilion is really not the best place to be. Another thing you want to keep in mind, the wind direction, because you can help prepare for it better, you can better shelter yourself. So now I'm going to pass it over to Rachel to talk about everyone's favorite, tornadoes.
All right. Hello, everyone. Thanks, Miranda. Thanks, Connor. And thanks, Mike C, for talking about all the other stuff before me. I'm going to be talking about tornadoes and then a few more weather hazards, and then we'll be wrapping up here shortly. So stick with us. I know there's about half an hour left. If you need to take a break or get a snack or something, you can stand up, stretch your legs, do whatever you need to do. But now we're going to talk about tornadoes. So I'm sure you've all heard of the EF scale. That is how we rank tornadoes, everything from EF0 to EF5. We actually can't rank tornadoes as they're happening, and we cannot forecast a tornado rank. Tornadoes are ranked only after they occur because they're based on the damage that they have done. So we can't look at a tornado that's happening right now and say, oh my gosh, that's an EF5. That's not possible. We have to wait until the tornado's passed in order to go out and survey the damage to be able to see, okay, what kind of damage is this? Is this just a little bit of damage, like some shingles got blown off the roof? Or are we looking at complete leveling of a neighborhood and there's nothing left and trees are splintered? So that would be obviously really, really bad. So tornadoes are only ranked after they happen. EF5 obviously is the most violent tornadoes at over 200 miles per hour wind speeds. They are the third most deadly form of severe weather. So that might surprise some of you. It's not the first most deadly, it's the third. So even though tornadoes are probably the most popular form of severe weather that people know about, that people talk about, that you hear on the news, they're actually not that deadly. We're going to go into talking a little bit about the most deadly form of severe weather here soon. But they are really amazing severe weather phenomenon. So most tornadoes are formed by supercell thunderstorms. Mike C talked about different types of thunderstorms we can see. And they can also be formed by mesoscale convective systems, or MCSs. Those are a little bit less common. They don't happen as much. we need the thunderstorm to be rotating in order to get a tornado, because the tornado is rotating. So if we don't have a rotating thunderstorm, or we don't have a part of the thunderstorm that's rotating, we're not going to get a rotating cloud that comes down to form a funnel and then a tornado. So tornado requires storm is rotating. So here are some examples. It might surprise you that you don't have to have the funnel cloud completely touch the ground, like look like it's touching the ground, for it to be considered a tornado. The definition of a tornado is that wind hits the ground. The rotating wind hits the ground and damage is occurring at the ground. So right here, we can see that there is wind and damage, because it's probably dust and debris getting spun up here, happening at the ground. So even though this tornado is invisible, it's still a tornado. So that's another thing that's really interesting about tornadoes, is they can be invisible. As long as rotation is at the ground, it's still considered a tornado. Tornadoes can have all sorts of different funky shapes and sizes. They can be elephant trunk tornadoes like this one, rope out, really, really skinny and long, or they can be fat and wide like this one, like stovepipe tornadoes. Sometimes they're really, really wide, and those are called wedges. That used to be a favorite of an old professor of mine. So they can have all sorts of different shapes and sizes, and remember, they can be invisible. So tornadoes are extra scary if they're invisible, because you can't see them coming. So Mike talked about shear. Shear is very important to get severe weather. If we do not have shear, we do not have severe weather. And there are two types of shear: directional shear and speed shear. So directional shear means that the wind direction is changing with height. We got northwest winds on the surface to northeast at the aloft. So direction is changing with height, okay? Like different little arrows stacked on top of each other of wind directions. Now, speed shear is when the wind speed changes with height. So we have slow winds at the surface and then really, really fast winds aloft. That can help generate what we call vorticity, or like a spinning tube near the surface. The earth and air do not actually look like this at the surface. They're not just tubes of atmosphere around hanging out at the surface, but just a visualization of what could be happening, some of the dynamics behind severe thunderstorms. So we need two different types of shear. Actually, we don't necessarily need both, but having them both can increase the likelihood that we're going to get severe weather. So if we're looking at a top-down view of this diagram here, the green one with the red mesocyclone showing spinniness happening, this is what a supercell would look like if we were a bird surveying it from space, looking down, and we were able to detect all the different little pieces of what's happening inside that storm. The light rain out here, and then heavy rain core with hail, and then even more strong hail closer to the updraft. And then this hook and this little arrow here where we have like a little indent, that's going to tell us that's where our mesocyclone is. That's where we have the rotating updraft, and that is where we're most likely to see the tornado. So again, we don't have like these tubes that happen at the surface, but if you were thinking about how shear can interact with the surface and create like a tube of vorticity, if that gets sucked up into an updraft from a very strong thunderstorm, that's how we can get a tornado. So if we have a really optimal environment where we have some shear setting up, increasing that vorticity at the surface, imagine that there are tubes, even though that's not completely accurate. There are some tubes at the surface maybe that are spinning, and then if they get pulled up by a thunderstorm updraft, then that's when we're going to get possibility of a tornado forming. So that's a little bit about how tornadoes can form. And obviously tornadoes can be extremely, extremely destructive. They turn things into missiles. A 2x4 goes through a house. That is insane. You've probably heard of the blades of straw that can get like launched into a tree trunk and then they're sticking out of the tree trunk. That is true. Tornadoes can turn things into missiles. They're over 200 miles per hour with the strongest tornadoes, so not something you want to mess with. Definitely need to be in a strong, safe shelter. These are examples of cars that have gone through tornadoes and obviously been rolled around and destroyed. Tornadoes are very sometimes skinny phenomenon. Sometimes they can destroy a couple houses and then not even touch other ones. So we can see here these unfortunate houses and neighbors have lost everything, whereas these houses further up the road don't even have a lick of damage. So tornadoes are not, sometimes they're really not large scale events. Sometimes they can be very, very skinny, very powerful events, but not over a large area. And then sometimes they can be over a large area. Sometimes they're a mile or more wide, and they can create amazing, amazing, incredible, horrible swaths of damage like this image on the bottom right. I mean, everything in its path is completely ripped out of the ground, destroyed. There's nothing left. So this is why we preach severe weather safety. We do not want you to end up in a situation like this. We want you to be taking the safety precautions so that you and your family and your friends can stay safe, and your pets. Pet safety is important too. So you can stay safe during severe weather and not have to live through this kind of situation. So tornado do's and don'ts. So if you have a tornado coming towards you, you want to get to the lowest part of the building. That is by far the best place to be is a basement. You want to get into your basement, find whatever part of the basement's most safe. Do not stand by the door if you have an exit out to the basement, out to the outside. Do not stand by your windows of the basement. Don't be looking outside waiting for the tornado. Not smart. Just get to the safest spot in your basement and hunker down, wait for it to pass. If you don't have a basement, get to an interior room such as a bathroom or a closet. Obviously no windows or no windows, sorry, to the bathrooms or closets either. Bathrooms are actually really, really safe to be in because all of the pipes in the walls help reinforce that room. So it's actually stronger than most other rooms in your house. So if you don't have a basement, get your mattress, get your pillows, get your blankets, go into your bathroom, get into the bathtub, cover yourself with your mattress and blankets, and that'll keep you really, really safe if anything were to fall onto you. You know, they'll protect you. You'll have your mattress or pillows on top of your head. Stay away from windows and doors. That has been said every single time we've brought up the do's and don'ts for severe weather. Don't want to be near windows or doors. They're vulnerable. They're places where air can get inside, where the outside can get inside. So you don't want to be next to anything where the outside can come inside, especially if it's a tornado. One myth is that people think that if you open your windows a crack, it's going to equalize the pressure in your tornado, or the tornado won't destroy your house. That is completely false. That will not save you. Tornadoes do not care. Usually the damage happens before the tornado even gets to your house because the winds are so strong that they're already sucking in your house as the debris is already being created. So don't open the windows. You're not going to prevent your house from being sucked up. It's actually just going to let more debris into your house. And one thing about tornadoes that is also not necessarily common knowledge is the wind is not the problem with a tornado. The wind is not the dangerous part of the tornado. What's the dangerous part of the tornado is the debris. So you want to protect yourself from all that stuff the tornado is picking up and making into a missile. Straw coming at you at 200 miles per hour is going to hurt you, even if it's straw. So protect yourself from the debris, stay away from windows and doors, get under something sturdy, cover yourself with mattress, blankets, or pillows, like I said. If you have a helmet nearby, put that on. That'll keep you the most safe if you don't have a basement to go into. So just do what you need to do to be safe. Do not hide under an overpass if you happen to be driving. They actually make the wind and debris go faster. Anytime wind goes under a bridge or under an overpass, it speeds up, kind of like the wind tunnel effect. So it is the wind tunnel effect. So don't go under an overpass. You're actually in a worse off situation if you do that. You're going to get into way worse conditions because that wind is going to be speeding up. You also don't want to shelter near debris sources like cars or trees. Stay away from trees. That's another big one. That kind of thing. So if you happen to be out driving, it's safer to drive into a ditch and be in the ditch than it is to be under the overpass. So just go to the ditch, go to the lowest part of the earth that you can get to. Do not open the windows in your house, like I said earlier. And of course, do not stand outside and watch the storm. I know it's interesting. A lot of us like weather. We're weather weenies. We like to go outside and look at the weather, but it's not safe. So do not go outside and just watch it. Do not just stand there and take pictures. Be a force of nature. That means go inside and be protected by it. We're building a weather-ready nation here, so we want everyone to be safe. If you happen to be stuck outside, be aware of heavy rain and flooding. So if you need to go into the lowest spot like a ditch, you don't want to also get flooded out. So if there's heavy rain and flooding, Maybe don't go into a ditch as your first spot. Go somewhere else where you can go that's pretty safe. But if you're not, going to get flooded away, or if there's no heavy rain that could create flooding, definitely be in a ditch, face down, cover your head, of course, always cover your head. And then, of course, get away from any debris sources. You don't want to be hit by any debris. That's the most important part. All right, so now we're going to move on to flooding. This picture was taken last year during some unfortunate flooding event in Lancaster. This poor cow is not having a good day. He's very fed up with the weather at this point. So we're going to talk about flooding. Now, flooding is the #1 cause of death for severe weather. So remember, tornadoes are the 3rd most deadly. Flooding is the #1 cause of death. Flooding is the most dangerous. That's why we have a saying in the Weather Service, turn around, don't drown. Turn around, don't drown. We do not want you to drive into flooded roadways because it is so dangerous. You don't know how fast the water is moving. You don't know how deep it is. It only takes 6 inches to sweep you off your feet. That's not a lot of water, and it only takes about 1 foot to sweep away your car. Again, not a lot of water to sweep away a giant vehicle. So do not drive into flooded waters. Most flooding deaths occur in vehicles. If your car happens to stall, get out, abandon it, go towards higher ground. Your car is not going to randomly or magically start up again as it's being washed away. You need to just escape and get to higher ground because #1 cause of death is flooding. Afterwards, avoid coming in contact with floodwaters. Flooding is super gross. It's a bunch of rain coming down, washing away all that trash and nastiness that's on the streets and sidewalks, and then being rushed towards you. So floodwaters are really dangerous. They're filled with disease and disgustingness, so we don't want to come into contact with them when flooding is happening. So just avoid it entirely, seek higher ground. Do not drive into flooded roadways, turn around, don't drown, please, please, please. And flooding can be caused by a variety of different things. So severe thunderstorms can produce torrential downpours. So it can be really, really fast amount of rain in a short amount of time, just torrential downpour all at once. But we can also have slow moving, persistent rain showers over the span of several days can also cause flooding. So June 3rd, Mike talked about this earlier, this derecho that came through. This was really, really heavy rain, as we can see by those red colors from the radar, that happened for a relatively short amount of time. And then behind it, we can see that there's more rain, but it didn't really last all day. It was kind of quick over in a couple hours. It was a lot of rain in just a short amount of time with all those red colors on the radar. In contrast, on June 11th, we have these little baby thunderstorms that keep just forming over the same area. This can cause a lot of problems if we just keep having rain over the same area. If the ground is saturated from just getting all of that rain from several days, then you're going to be more prone to flooding. So you don't necessarily have to have a torrential downpour to cause flash flooding. Sometimes just slow, persistent rain showers over the span of several days. Also, you don't even have to be in the area where there's a thunderstorm. If you live next to a river, there's a thunderstorm, north of you, upstream, and it dumped a bunch of rain there, all of that water can be coming down through the river and then flood you later. So that's another thing to be thinking about. If you live near a river, if you live in a flood zone, just be aware of what might be happening elsewhere that could affect you in a later time period. So we're going to take a look at why you should never drive on a flooded roadway. I'm very passionate about this. I'm passionate about safety. This is a video of a flooded roadway in Maine in 2008, and we're going to see what happens when water goes over the road. So not only is this water moving incredibly fast, you probably don't even realize how fast it's moving if you were just standing on this roadway or going to try to drive over it, but there is a lot of it. So it could wash you away quite easily. We don't want that to happen. It's already starting to destroy part of the road here. What's happening in this situation is there is a drainage pipe underneath the road that's supposed to get rid of flooded roadways, water on the road. But obviously there's a lot of rain here, a lot of water, the drainage pipe is full, and now the water is on the roadway. So let's see what happens when we get too much water on a roadway. I might speed it up here just for a little bit. You can see there goes a tree. Part of the road is starting to erode away here. Now those trees are disappearing. Where are they going? They are going underneath. Not a good sign. Not all roads have a drainage system that goes underneath them, but more often than not, you might not even know if roads have a drainage system that go underneath them. So it's better not to take the chance. It's better to find a different route, different way to go home. We can see that part of the road just fell off there and collapsed. Asphalt is not a complete solid object. It is a putty, so it will bend and flex with force. So that's why the road is breaking apart there. You can see more roads starting to break apart. I'm going to speed up here a little bit so we can get the gist of it. More road slowly breaking apart here. Not a good situation. And there we go. Road is gone. So if you were trying to drive across this road, you would not be successful. The road is gone, and it's going to continue to disappear because that rushing, raging river is still flowing. There's still flooding going on. The flooding hasn't ended. The drainage pipe is going to pop up here in a sec, and you'll see what was actually supposed to be under the road is now going to float away. So more of the road just keeps eroding. Bye-bye. So turn around, don't drown. You don't want to be a car driving into this and then washed away because there's no more road left underneath you. And then, yeah, there's the drainage pipe that floats up to the surface. So stay safe. Don't drive into flooded roadways. You heard it here first. So where to go, what to do. Get to higher ground, tall, stable building. If your house is flooding, leave. Get to a higher ground, somewhere safe. Turn around, don't drown if you're driving, and of course avoid floodwaters. They're gross, they carry disease, you don't want to get sick. So what not to do not go towards the floodwaters, pretty self-explanatory there. Do not drive on flooded pavement, you don't want to end up on that road that collapsed. And then of course do not drive over bridges because that's a higher risk that something bad could happen, like what we just watched in the video. Now I will pass it off to Connor to talk about extreme heat.
Thanks, Rachel. Yeah, I'll take over the PowerPoint here. There we go. Okay, yeah, so extreme heat. So you're probably all familiar, you've probably heard about, oh, it's not that hot today, it's a dry heat. Maybe folks comparing retiring in Arizona versus retiring in Florida. Folks saying, 100 degrees in Arizona beats the heck out of 85 degrees in Florida. And when you're hearing that, when you're talking about that, what you're really getting at is the heat index. The heat index is kind of, if you ever heard of like the real feel or the feels like temperature, it takes into account humidity into the temperature. It's not the heat that gets you, it's the humidity. There's truth to that. I know it's an old saying, but there's a lot of truth to it. In that humidity affects is one of the factors that can affect our body's ability to cool ourselves off and thus make it feel a lot hotter. I'll get into that more in a second. So if you ever hear the dangers of heat, heat stroke, heat stress, so forth, dehydration is another one too. Those are some of the real dangers that are associated with extreme heat. And just like when we're talking about whether it's hurricane awareness, ensure we don't get hurricanes landfalling in Pennsylvania because we don't technically have a coast. We can get the rainfall. We can even get the wind. Same thing with tornadoes, as Rachel was just talking about. We don't get tornadoes as frequently or often as powerful as parts of the Midwest, but we do get them, and we definitely get them enough to make it something worthwhile being prepared for. Extreme heat, you might think, oh, we're Pennsylvania, we're not the South or the Southwest. Anybody who's been in here, particularly the southern half of the state, really all of the state during the June, July, August, can tell you very quickly it can get hot, and it can stay hot. Thinking back to last summer, 2020, wasn't so noteworthy in that we were breaking records left and right of 100-degree days or anything like that. But July of 2020, we had I'm drawing a blank how the exact number of 90-degree days, but a couple dozen and more in Harrisburg area, and more days than not in July hit 90 degrees in some parts of Pennsylvania. So combine that with humidity, it can get toasty here, and that's why it's super important to prepare. If you're doing outdoor activities, you're traveling, and so forth, making sure you're prepared with water, and making sure you're taking breaks in the midst of your work and so forth too. Definitely something worth preparing for. So as I mentioned, really important to stay hydrated in extreme heat. I have with me when if I'm doing yard work, something outside, I have a big jug of water that I carry with me. If you think of the gigantic Gatorade bottles that sports coaches get covered with at the end of the game when they win, I have a mini version of that. Holds I think like 3/4 gallon of water, and just go back and forth to drinking that I'll carry, or if I'm traveling, I bring that with me too, just to make sure I'm staying hydrated. Or sunscreen is very important too. Important whether or not whether it's 90 degrees or 65 degrees. We're getting to the time of the year where the sun angle's so high. The sun right now is the same position that it's in about mid-August for perspective. We hit that peak sun angle at the summer solstice in late June. But this really right now is high sun angle time. So always important to, if you're outside, spending some time in the sun, doing yard work or going outside on a run or anything like that, very important that you cover up exposed areas with sunscreen. Light colored and loose clothing. So there's a term that any meteorologists in the room or folks who maybe taken a class before or fellow weather weenies might be familiar with. It's called albedo. And albedo just refers to the reflectance of a surface. So if you think of something like asphalt or even water, these are what we call relatively low albedo surfaces in the sense that they don't really reflect as much of the sun's radiation. They're really good absorbers in the sense that that asphalt can still be decently warm even after the sun's down. And water, is really absorbing of heat, particularly when the sun angle is high. Compare that with snow. If you ever walked outside on a sunny day in the middle of winter and there's fresh snowpack, you're going to need sunglasses. It's so bright because all of that, nearly all of the solar radiation that's hitting that snow is getting bounced right back up. Essentially, it's not really being absorbed by that. So really high albedo surfaces. And so what that comes down to, typically, darker surfaces, darker materials tend to be more absorbent, and lighter materials tend to be more reflective. So I can say, I mentioned a couple times in a flooding talk a month ago about stories of flooding around the time when I got married in Lancaster County. Well, the actual day of my wedding was late July. Now, I've lived in Pennsylvania for a few years, but a lot of my friends, my groomsmen, they're from upstate New York. Doesn't get us hot in the summertime. It's late July, and we're getting our pictures. We're all in our dark suits, 3-piece suits, and it's 12:30 in the afternoon. Sun's beating down on us. It's low 90s. It can get warm. And what made it all the more worse was wearing black suits because that can exacerbate some of the absorption of heat from the sun. So if you have some lighter, loose clothing, absolutely, that's breathable, so athletic wear, so forth, and lighter color. Think of the lighter greens and yellows and whites and so forth. Seeking shade. If you're like me, the summertime, I like to bring my work outside from my laptop, or if I'm hanging out reading a book. Get some shade to protect yourself from sunburn, but also just to get a little cooler, to make sure you avoid dehydration and so forth. And reducing physical activity. It's a very, very important one. We think, I have plenty of energy in me, so forth, but you're gonna increase your body's internal temperature. You're gonna increase the amount that you're perspiring and so forth. That puts you at risk for heat-related illness. So you may want to, if you're a runner, or to get your exercise in, try to do it in the earlier parts of the day, or in the evening. But dawn, if you're an early bird, is the best time to do it, because that's typically the coolest time of day. And when we're talking June, July, August, sometimes the coolest time of day only cools down to 70, 72 degrees in the warmer times of year. So you want to take advantage of those cool times for physical activity, or maybe plan your gardening and so forth for the early morning hours of the day. So this is the heat index I was talking about. So we're coming out of cold season. We're not entirely out of cold season. In fact, our neighbors over in northern Ohio may be picking up a couple inches of snow to tomorrow night, in parts of Indiana too. So April is the transition time of year, but thinking winter, the real feel that we look at is wind chill, and that brings in air temperature, but also calculates a metric based upon the wind speed. So I don't know the exact formula in my head, but you can think that 30 degrees with 20-mile-per-hour winds probably is a lot more uncomfortable than 20 degrees with no wind. It brings that into account to what the apparent temperature is, and also risk of frostbite and another cold-related illness and injury. Heat index, just like wind chill, it's based off of the temperature, but instead of wind speed, take into account relative humidity. And that goes back to the whole, dry heat versus humid heat. And this is a chart right here. The formula is not there if you're really into the math and so forth. You can find the formulas online. But this basically shows you, if it's a 90-degree day and relative humidity is, 50%, it's in the hot area. The heat index is, pushing 100-degree heat index there. That's what it really feels like there. So it's helpful to keep in mind, again, why sometimes dry 90 degrees is better than a humid 80 degrees. And that's always included in your standard weather service forecast. You can see if you're checking, what's the temperature outside. If you go to the weather service website, it'll say here's the temperature, but also here's the heat index. So something you'll definitely want to keep in mind to dry 85-degree day. Okay, if I'm staying in the shade or something, go outside. If it's wicked humid outside, maybe I'm gonna see if I can do my work inside, or plan accordingly, because it's gonna feel really, really warm and might be really poor working conditions. Wet bulb globe temperature. Say that 5 times fast. So essentially, this is a metric, kind of like heat index, but builds off of that to basically account for your body's ability to cool itself. So it brings in temperature and humidity, but also brings into account the sun angle, so the time of year. So if you think of, June, late June, when the sun angle's highest in the year, summer solstice, versus say early October, it's possible to get hot temperatures in early October. It was 2019. October 1st or 2nd, some parts of the state were pushing, I think may have actually hit that 90-degree mark. So rare, but it can happen. But you think of by then, the sun is way lower in the sky, because you're getting into autumn there, than it is in June. And so that's going to factor into how your body perceives the heat, essentially too. Wind speed. So you think of, if it's a hot day but you have a nice breeze cooling you off, it's going to feel a lot better and help you cool off a lot better than if it's stagnant. There's no breeze at all. So it's a metric that brings all of this stuff together to basically answer the question of how well is my body going to be able to cool off and cool itself in hot conditions. And so again, the formula, if you're interested, it's available online. I wanted to want to spare you the details and give you the nuts and bolts of what's important. But yeah, it gets to the fundamental of how well will my body be able to cool itself off. And interestingly enough, this is an area of growing research in some academic fields, including geography, where I'm coming from, of parts of the world that, due to increasing warmth, they're approaching wet bulb temperatures that are nearing the threshold of where a body can no longer cool itself naturally. It's getting too warm, basically where ideally our body is trying to shed heat into the environment when we're trying to cool off when it's really, really hot in the summertime, where the ambient, the outdoor temperature and all those variables together are making it so the body can't cool itself off. In fact, it's continuing to absorb heat. So, and that's when you're looking at the threshold of, okay, no longer humans cannot live or survive without some sort of means of adaptation. So certain climates at certain times of year where it's just, you just gotta stay inside. You just can't cool yourself off. And so some weather service offices are using wet bulb globe temperature experimentally and are starting to implement it as an additional forecast product. And you can find it. It's not listed necessarily like heat index would be, like right on your standard weather service forecast, but you can find it. And the biggest thing, in my opinion, to look at, besides just like what the wet bulb globe temperature is think about the color code. Kind of we've looked at things in the past. If you've been with us before for some of the talks about like severe weather and flooding and so forth, the color codes of green being low risk, and typically when you're getting to the reds and the pinks, that's when you're seeing high risk of flooding, severe weather, whatever it be. So high risk here for heat-related illness. And so as we're working our way up here, if you have a wet bulb globe temperature 90 or above, you can get heat stress within about 15 minutes. And so precaution is 3/4 of every hour, 45 minutes for every hour, you should be taking a break or getting outside of sunlight, because your body needs that in order to keep functioning and not to become ill. Because heat stroke and heat stress can be very, very serious. Here's a map from, when was this? This was last year. Yeah, so you can find these maps, I believe, on the website of wet bulb globe temperature. The reason why I say I don't want to say completely disregard the temperature reading there, but just so you don't get confused by seeing, okay, 84 degrees in Du Bois, that's nothing. 84 is fine. It's not the actual temperature. It's the wet bulb globe temperature. So very likely the temperature is a lot higher than this. And why I say don't be deceived by the 84 is because right now we're in the high, nearing the extreme along the wet bulb globe temperature, going back to that chart from the last slide of where, hey, if you're working outside, if you're doing any sort of work, you're really going to want to be working in few minute spurts before you go get some shade, drink some water, do what you need to do, because temperature, in addition to probably lack of wind, high humidity, high sun angle, like this is June, so high sun angle, all those factors together are going to make it really difficult for your body to cool itself off. Your body's going to be doing a lot of work just simply to sustain itself, to where you're going to want to take some sort of adaptive measures to cool off and to seek relief from the heat. And yeah, I'll pass it off for them to finish up with products and services.
All right, hello everyone again. I know we're past 8:30 here, so we're gonna go kind of quickly through the last little bit here. Thank you to everyone who's stuck on this far. So just overview of severe weather outlooks. We will issue these different products to help you understand what you can expect a few days out, day of, and then immediately before the hazard is about to happen. So An outlook is going to give you kind of an overview in a few days or maybe tomorrow. Maybe you can expect some severe weather in your area. A watch is probably going to happen the day of, probably a few hours ahead of time, a few hours before those storms start to pop up. Okay, yeah, maybe we expect thunderstorms or tornadoes. You know, maybe we have a tornado watch over our area or a severe thunderstorm watch. We will be issuing that a couple hours to about a day or several hours ahead of time. So day of event, certainly. And then a warning is when your hazardous weather is imminent or ongoing. That is when you are in that little box, if it's yellow or red, and you are in danger of whatever severe weather event is coming towards you, whether that be strong winds or hail or tornado. So you want to definitely be taking action at this point. You want to be past the awareness and the preparation stage. You want to be taking action, getting to your safe shelter. So here's some examples of what the outlooks look like. Outlooks cover a large area. So we can see for Pennsylvania, there's a marginal risk here. Actually, sorry, this is the general thunderstorm risk here. The marginal is the dark green. And we can just see here, this is a large area. We might see some general thunder in Pennsylvania. As we get closer to the event, we're going to get narrow and narrow down because we can kind of piece out where it's going to happen and get a little bit narrowed down like a funnel into where we expect the severe weather to happen. So understanding thunderstorm outlooks, light green, just general thunderstorms. Expect there to be thunder and lightning, maybe some small hail and some wind gusts, but you're not going to see your extreme deadly thunderstorms with this. As we increase in outlook category, marginal, slight, enhanced, moderate, and high, we increase in severity. So you can expect winds to pick up, hail to get larger, and then the tornado threat to increase as well. So since we're running low on time here, I won't go too much into the weeds or the details with this, but if you're interested in learning more about thunderstorm outlooks, I encourage you to watch some of our Skywarn spotter talks. We talk about this in detail. And then also go to the spc.noaa.gov. They've got some great resources there. You can learn more about that and start following your thunderstorm outlook, as they've been starting to be, they're issued every day, no matter what type of season it is. And now that we're getting into severe weather season, you can pull that up every day and briefly look at it and see what the Storm Prediction Center is predicting for severe weather today or tomorrow. Similarly, flash flood outlooks are issued as well. It's a similar kind of color table here, except now we're talking about flash flooding. And this will go from marginal, slight, moderate to high. And these will outline where we expect flooding to occur. So this is for June 16th of last year. We can see that there's some slight flooding expected on the East Coast here, and then some marginal in the West. And if we ever have a bullseye of slight or moderate flooding in Pennsylvania, you can expect there's going to be a lot of rain. That's probably going to contribute to that flooding. So that's definitely something to be thinking about. If you're interested in learning more about this, you can go to the weatherpredictioncenter.ncep.noaa.gov, so wpc.ncep.noaa.gov, and then you can get more information on that and also get your flash flood outlooks. So watches versus warnings. Watches tell us the weather conditions are favorable for a phenomenon to occur. So you want to be alert to worsening conditions, know how and where to take your shelter. We've talked about that. And then a warning is a much smaller box. So watch is taking up pretty much all of Oklahoma in this case. And then a warning is a much smaller box. It's taking up just including a few cities. So Oklahoma City, you know, if we zoom in here to this top photo, we can see Oklahoma City is just a little blip right there in the center of Oklahoma. But now we have our warning out for this beautiful supercell. We have a hook echo. We can expect there's a tornado. Act immediately. We have detected on radar that the phenomenon is occurring. So you want to act immediately. And of course, warnings take up a much smaller area than watches, because again, as we get closer to that event, we're zooming in into the scale. So we're getting honed in into that details and where it's happening. So severe weather safety, you want to stay weather aware always. So always have a way to receive warnings and alerts. This could be with your Noaa weather radio. I know it's a little bit old school, but Noaa weather radios are really great to have because they will go off no matter what time of day it is. If you are sleeping at 3 in the morning and there's a tornado coming to your house, the weather radio is going to go off and let you know, wake you up so you can go to your basement. Not all phones are going to do that. So you want to make sure you have a way to receive warnings even when you're vulnerable, like you're asleep in your bed. Another way is also with a phone, an app, etc. If you have a smartphone, here are some useful apps that you can download to get weather warnings. So FEMA is my favorite. FEMA, you can sign up for any type of alert that you want to get. It doesn't have to be just weather related. It could be terrorist activity, other non-natural disasters. But a lot of them, of course, a lot of disasters that occur are natural disasters. So like a thunderstorm or tornado. So anytime the National Weather Service is issuing a product for your area that you select through the app, you'll get a little notification that comes up on your phone. Okay, Weather Service has issued a frost warning, for this area. And you can choose different areas that you want to focus in on. So if you live in central Pennsylvania, you want to focus in on central Pennsylvania, great. But maybe you have friends or family who live like in Chicago, like me, and I would like to know what the weather is doing in Chicago in case I need to tell my family or friends what's going to be happening. So you can choose different locations to get your apps and notifications directly to your phone for anything that the Weather Service issues. And if there's other issues or disasters happening near you, you'll get your alert. So automatic warnings and important messages. Also go to mobile.weather.gov. The National Weather Service does not have a weather app, but we do have mobile-friendly web pages. So if you go to mobileweather.gov, you can type in your zip code, your city, your town, and you'll be able to find your forecast directly for what you need. So search for your location, weather forecast to get important updates. And then radar apps are really helpful to use. We can't endorse one particular radar app that you should use, but radar is obviously a really good tool to understand what's happening by looking at where the strongest rain is happening, where maybe hail could be occurring, how close is it to you, is it almost done, that kind of thing. So find a radar app that you like, pull it up on your phone, and then see what happens. Watch what's going on in your area. So real-time radar information and warnings will also usually pop up on your radar too, so you can see if you're in the warning and how much longer you'll be in the warning for. So last but not least, we couldn't finish off a Weather Ready Nation lecture without talking about becoming a Weather Ready Nation ambassador. So what is a Weather Ready Nation ambassador? It's an organization that promotes Weather Ready Nation messages and themes to their stakeholders. So if you're an organization and you have a lot of stakeholders, you have a lot of customers, you want to promote weather readiness to them, I encourage you to become a Weather Ready Nation ambassador. You encourage or engage with Noaa personnel and potential collaboration opportunities, which is really cool. You serve as an example in your community by educating employees and making sure your workplace is prepared for different weather events. And then you also want to share your success stories with us when you're a Weather Ready Nation ambassador. What have you done that was successful for making sure your employees or your community was weather ready for a particular event? So if you want to become a Weather Ready Nation ambassador, head over to weather.gov/weatherreadynation, WRN/AMB-TOU. If you just Google Weather Ready Nation, you'll be directed to the website, and there will be all those different tabs at the top where you can select become an ambassador. So I encourage you to check that out. If you are a current ambassador and you're tuning in to watch this presentation, of course, hopefully you're setting an example by making yourself weather ready, your community, your organization, and you're promoting these Weather Ready Nation messages through your outreach activities, and then also providing incentives to your employees and stakeholders to become more resilient to weather and become more weather ready. And then also we want to hear your success stories. So if you are a current ambassador, we will be hosting another lecture probably in a couple months here where we are going to solicit your feedback and ask you your success stories for being an ambassador and spreading the word and spreading the awareness. So if you're not an ambassador, this is something you're interested in doing, and this is something you would like to participate in, please look it up and think about becoming an ambassador. And I will send out more information about this later to those of you who may be on the fence about this and not quite sure. And then if you are an ambassador, we want to hear from you. We want to know what has been successful to you, any success stories that you particularly had with building a more weather resilient community. So find us online. We're all over the social media. We have a new Instagram at NWS State College. We're on Twitter, we're on Facebook, we have YouTube, and then of course, get our forecast at weather.gov/CTP. So we are all over the interwebs. Please check us out, follow us, get your weather information, contact us. We'd love to hear from you. And with that, I will invite all of my speakers to come back and we can start taking questions. So thank you to everyone who hung on. About 17 minutes passed. Appreciate it. And if you have any questions, you can bop them in the chat box. If not, thank you for hanging on, and we appreciate any feedback you might have for us. I'll be sending out an email after this with a Google form where you can tell us what you liked and what you didn't like. We appreciate any feedback that you can give us on that. All right, I see some kudos coming in. Thank you everyone who's thanking us. We appreciate it. If you didn't get a chance, download those handouts in the handout section for your own reference. Ooh, good question. What's the difference between sleet and grapple? So sleet is a frozen raindrop, and grapple is a snowflake that's collected supercooled liquid water. So sleet is something that's already completely melted and then refroze. And then grapple is when you already have that frozen particle, that snowflake in the middle, and then it's collecting water that's freezing. Someone asked, is a large piece of construction equipment safe thing to hide under outside in a tornado? I would say absolutely not, because construction equipment can be really, really sharp and dangerous. And if it's lofted, if it's turned into debris, you don't want to be underneath or near it if it's going to come crashing down on you or propelled at you if it turns into a missile. So I would say not a safe place to be. All right, questions have kind of slowed down. We're going to close in about 2 minutes here, so if you have any last minute questions, feel free to plop them in the chat. Otherwise, thank you again for attending. I don't know if any of our other speakers would like to say anything as we wrap up here. Oh, if you're hiking on a mountain and a thunderstorm comes, that is a great question and a really tough question because if you're on a mountain, you're closer to getting struck by lightning. If you're by trees, you're at a higher risk of getting struck by lightning. So if there's a rock that's forming some sort of like cave, that would be a good place to go. Try to avoid the trees if possible. If you're in a forest, you need to do what your gut's telling you to do, your best judgment. If you are on top of a mountain and there's nothing around you, you are the tallest thing out there, that's also bad because you could get struck by lightning. So in that situation, probably want to crouch to try to not get struck, or at least lower your chances of getting struck. But yeah, definitely not a good situation to be outside hiking in a thunderstorm comes, so check your forecast before you go hiking. That's my biggest recommendation.
Yeah, I'm going to echo that as well, because I know out in Colorado and some other states, hikers are struck by lightning so often. Colorado in particular, because they get so many afternoon thunderstorms during the summertime. So it really is important to not get yourself in that situation. Check the forecast before you go out. And then as a very, very last resort, there is that lightning crouch that Rachel mentioned. If you want to get down as low as you can to be as small of an object as possible, and also minimize your contact, the contact between your feet and the ground itself by kind of crouching up on the balls of your feet. But that's an absolute last resort. You really want to check the forecast and not get there during a thunderstorm.
Yep. All right. I see 8:52 on the clock. So thank you all again. Thanks for the great questions. And with that, we'll close. So thank you to our speakers for an excellent presentation, and hope to see you at the next one. Bye.
Thanks, everyone.